So I've kind of been downplaying the usefulness of spatial hashes as a way to hierarchically organize your collision world. And now that I've actually sat down and messed around with them pretty in-depth while I was planning these videos out, I actually like them quite a lot, and I think I've actually changed my mind in that spatial hashes are probably a lot more useful in more situations than other hierarchical structures that I've talked about in the past, such as, quadtrees or octrees. So what is a spatial hash? So quadtrees and octrees and other k-dimensional trees work by partitioning the world in half a bunch of times, and then you can recursively search the section of your world which you are interested in for collision checking purposes, and you can narrow down the part of the world that's actually relevant to your collision checking. And this allows you to cut down from potentially a larger number of collision objects to just a few. And certainly, as we've seen so far in the series, that works pretty well for a lot of cases. And spatial hashes partition the world a little bit differently. So instead of subdividing the world in half a bunch of times, a spatial hash will instead essentially divide the collision world into cells of a grid. And instead of recursively traversing a k-dimensional tree to figure out what part of the world is relevant to your collision detection, spatial hash will just allow you to check one or more cells in the grid encompassing the entire world, which are relevant to your collision detection based on the bounding box of the collision shape as a whole. And I'm sure I'm going to be talking and comparing and contrasting the two different collision strategies more as these videos drag on. But let's dive into getting some things set up first. So first, before I write any code that's actually relevant to spatial hashes, I'm going to need to do a little bit of maintenance again, as I've had to do several times in this 3D collision series. I was using this system in my follow-along game dev project of a 3D wizard game, and I found a couple of bugs in the vector 4 multiplication division, and I think vector 3 multiplication and division. No, those two are fine. So in vector 4 multiplication and division, I, from the looks of things, copied and pasted something and forgot to make a particular relevant change. So if you're multiplying a vector 4 by a scalar, just multiply w component by the scalar. Don't try to extract a w component from a scalar. Not how scalars work. So I'm going to just real quick fix that. Also, as the series has dragged on for almost 2 years now, and GameMaker has received some updates, there are some bits of GML that you can do that will simplify things a little bit. Particularly when it comes to, at least the one that I have in mind, is when it comes to searching an array for a value. So if I have a quadtree or an octree node, and I want to remove something from a quadtree or an octree node, I am currently looping over the array, searching for that item, and then if that item is found, we continue doing this recursively. And GameMaker Studio, I believe 2023.1 or 2023.2, I can't remember the exact version, added the array get index function, and this is just an array search. So you can pass it an array, which in our case will be self.contents. You can pass it a value to search for, which in our case will be just object. You can optionally pass it some parameters for a start and a length, and a start and a length if you only want to search part of the array. And this will return the index of the array at which that item has been found. And instead of having to do a for loop or some other loop over the entire array and doing it yourself, we can simply say if index is not equal to -1, then we can array delete from our contents the value at that index, and we're just going to delete one element. And from there, we can continue recursively moving elements from our data structure. And that'll be infinitesimally faster because letting GameMaker search an array is faster than you searching an array. And it's also just like a little bit less code. And I definitely appreciate having less code when I can get away with it. Let's see. The quadtree, I believe, is going to have something similar going on here. And if you'll give me a moment, I will implement the same update to the quadtrees remove method. All right. Is it worth checking if there's any other instances of doing this sort of thing? Doesn't look like it. Alright, so that's the only section of this project where array get index will be relevant. I'm sure there are other pieces of code in this project that I can update like that, but this one was just on my mind because we're going to be writing similar array searching code for spatial hashes, and I just wanted to put that a little more front and center. So let me commit these changes. Okay, so that's been established. I can start writing code for actual spatial hashes now. So I'm going to create myself a new code file, and we can call this call underscore spatial underscore hash. First, I'm going to outline exactly what methods a spatial hash is going to contain. Spatial hashes are going to have an interface that looks an awful lot like just any other call world for an octree or a quadtree or anything like that, but it's going to work a little bit differently internally. It's not going to be exactly the same. It's not going to be exactly the same interface, but it should be familiar if you've been following along. So I'm going to start with a, let's call it call world spatial hash. And that can be our constructor function. I'm going to give this a single parameter. I'm going to give this a parameter that's for chunk size. So each of the cells in the spatial hash, each of the buckets, if you will, they can have a certain size to them. I'm just going to make all of these cells like a square. So they're not going to be longer on one axis than any other. You can make them not squares if you want. I don't have any desire to make spatial hash cells anything other than squares. And that's going to differ a little bit from the k-dimensional trees. I'm just going to call them that because it's easier than saying quadtrees or octrees all the time. Because we're not taking a bounds, spatial hashes could be infinite. They will expand as needed. And we are not going to give it a recursion depth because spatial hashes do not recurse. So first, let's save our chunk size parameter to an instance variable. So we're going to remember that value for later. Next, I'm going to have an empty struct. So this is just going to be an empty, basically a lookup table. Hash map, hash set, whatever you want, containing, I guess it wouldn't be a hash set. Hash map containing all of the cells that have things in them in our spatial hash. And I'm also going to, and this isn't strictly part of the spatial hash, but this is just going to be for my convenience. I'm going to call it self.bounds. And this is going to be an access line bounding box that encompasses the entire structure. And I'm also going to say, I'm going to call object record. And that's going to be another empty struct. And that's going to be basically keeping a record of every object that is in our spatial hash. Next, something else that is going to be for my convenience. I don't actually know how other implementations of spatial hashes deal with this, but spatial hashes, anything you put in a spatial hash has to have like a finite size, and they can't be a shape that's infinite in some direction, which is to say, in our case, that's going to be arrays or planes. And I don't know how other people deal with this necessarily, but I'm just going to create basically an array for planes, and this is just where we're going to store planes. For those, if you want to detect collision with, you can just iterate over the array like normal. It's unlikely in practice that you're ever going to have more than like a couple floors, like a couple infinite planes in your collision world. Anyway, let's see. I'm going to start defining methods. I'll give this a debug draw. I'm probably just going to fill this in myself without narrating my way through it. It's going to look a lot like the debug draw in some of the other data structures. I just want a way to visualize this so that you can see exactly what shape this data structure is taking as we go. I'm going to define a method that is going to be static hash function. This is going to be a function which I'll fill in later. It's going to take 3 parameters, x, y, and z. I'm going to define a method that is getBounding chunk. That is going to be a function which takes an object as a parameter, so any old call object, and it's going to figure out basically a bounding box around it. I'm going to define static getChunk, and this is going to be another method that's going to take an x, a y, and a z. That is not a semicolon. I'm going to define static add. You should be familiar with what this does. We can say static remove. We should be familiar with what that does. Static check object. I think you guys know what the deal with that one is. And lastly, static check array. And that is going to be a method for ray casting, which is going to take array, and it is going to take a collision group. Oh, and I think I'm also going to want to remember to include the optional collision group parameter to the check object one as well.
Hey.
So those are going to be all of our relevant methods for a spatial hash. All right. Next, I'm going to need to define the spatial hash nodes. So our quad trees, our octrees, our whatever k-dimensional trees, they were comprised of nodes, which are recursively subdivided. And spatial hashes will also have nodes, but instead of recursively subdividing them, they're simply going to be basically the cells in the grid, as I've been calling them. I'm going to say var, a function call spatial hash node. That's going to take a parameter to the constructor, which is going to be its bounding box. So that's going to be where it is in the grid, as it were. We are going to have a list of objects. It's going to be initialized to an empty array. I'm going to start defining methods, so I can say again debug draw. And I'm probably going to fill that in on my own, as I said. And then we can simply say add, remove, check array, and check object. And instead of typing all that out again, let me just copy and paste. So that's going to be our spatial hash node. Also, raycast for spatial hash nodes will take a hit info struct to which we can pass the output results to. And it will, the method itself will return a Boolean, whereas checkRay for the spatial hash as a whole won't do that. CheckRay for the structure as a whole will simply return the hit info, whatever that happens to be relevant to. Okay. I did not spell nodes right there, did I? There we go. So continuing on with the initial setup. For spatial hashes, each of the shapes that we can add to the data structure, to the hierarchy, is going to now need methods for getting the minimum and maximum bounding box of that shape. And some of these shapes already have something like that. So call ab, GetMin, GetMax, we've used that for quite a number of things. I believe, does call ob have that as well? I think I did for call ob as well. It actually looks like I did not. I did not. Cool. I think in a lot of cases, if I didn't strictly need a GetMin or GetMax for a particular shape, I didn't add it. If I knew that I was going to be making such a big deal about spatial hashes like way back at the beginning of this 2 years ago, I would have, but alas, hindsight's always 20/20. There's sort of a convenient data to have about shapes in general anyway. So let me go through and implement the GetMin and GetMax for all these shapes. Some of these are going to be a little bit easier than others. So if we go into call point, for example, this is going to be so trivial that it's almost a little bit comical, but I can say static GetMin and static GetMax. And as it turns out, the minimum value, the minimum coordinate of a point is going to be self.position, and also I'm going to need to return that. As it turns out, the maximum coordinate, the maximum value of a single point in space is also going to be self.position. So yeah, as I said, that's going to be a little bit comically simple.
Hey.
If I were to go into, on the other hand, call shape ray, this is one of what I mentioned as being an infinite shape. Because rays extend off into infinity. There can be a minimum or maximum point of a ray, depending on which, like what direction they're going in. But I'm not going to bother working that out. I'm just going to say a raise, GetMin, and GetMax are going to be undefined. You're probably not adding raise to your collision world regardless. What else do I have? The other infinite one is plane. So I'm just going to give that an infinite minimum and maximum as well. And then we can start getting into some of the other shapes. So a sphere, for example, you can probably work out what the minimum and maximum values of a sphere are. Sphere is being defined by a point in space and a radius. Self.position.sub, self.radius is going to be our minimum point for a sphere. And the maximum point is going to be add. Working this out for a line should be pretty easy. Not what I meant to copy and paste. I meant to copy and paste the whole thing. For a line, we can return a new vector 3, which is going to be the min of, what are they? Start and finish, self.start.x, self.finish.x. So the smallest x value on our line. Minimum of self.start.y, self.finish.y, min of self.start.z, self.finish.z. And that's going to be our minimum value, and the maximum value is going to be the max of each coordinate instead. That makes sense, right? Capsules are built on lines. Capsules are built on top of lines. So to do this, to work out the minimum and maximum point of a capsule, we can say return, it is self.line, right? All right, self.line. Self.line.getMin.sub. Self.radius. So a lot like a circle, a long circle. Did I say I was going to stop making that joke? I lied. What else do we need? We've got abs, capsules, lines, meshes. Meshes keep track of their own bounding box, right? So, okay, so meshes know their bounds relatively, so that'll just be self.bounds.getMin. This is a little bit, maybe a little bit not ideal, because we are figuring out our minimum and maximum bounds up here, and then saving that to the bounds value, and that's converting it into an ab, and we're kind of converting the ab back into. All right, you know what? This is a little bit silly. So instead of making those a local variable that evaporates after the constructor is finished, we can save the minimum and maximum point too. All right. Let's see. Obs are going to be a little bit more involved, I think. That's going to involve a little bit of vector math. Planes we dealt with, points we dealt with, rays we dealt with, spheres we dealt with, triangles. Triangles are a lot like lines. So I think I'm actually going to copy and paste the line min and max and apply that to triangles, because triangles are, instead of a start and a finish, they're just going to be an A, B, and C. So I could say self.a.x, self.b.x, self.c.x. And we can do that for the x, y, and z each respectively. Self.a.y, self.b.y, self.c.y, az, bz, and cz. And when it comes to GetMax, we can do the opposite, so we can get the biggest of those values. So that's going to leave the matter of ob and transform model. I think I'm going to do ob first. Ob. This is going to involve a little bit more math. Fortunately, we have already in ob a get vertices method, and while it's not going to be super efficient, unfortunately, to call the get vertices method every time you call GetMin and then iterate over that to find the smallest vertex, and GetMax and do the same thing. The alternative is basically going to be to do the same operation over anyway. And there isn't, as far as I know, like a nice, convenient, easy way to do this. So we can say var vertices is going to be self dot get vertices, loop over the vertex array. We are going to want to figure out what exactly the minimum, the minimum value is. So we'll define ourselves a new variable that's going to be point min, and we'll initialize this to a new vector 3, which is going to have values of positive infinity, positive infinity, and positive infinity. And every time, for every vertex in the vertex array, we can say point underscore min dot x is going to be equal to the minimum of point underscore min and whatever the current vertex dot x is, and we can, yeah, thank you, Feather. That needs to be point min dot x. Feather's finally really earning its keep here in these videos. It's been part of GameMaker for well over a year now, but I've only started leaving it on for these recently. So we can update the minimum point on each of the axes for every vertex. I want to say something similar was done in the mesh shape. Yeah, something similar was done in the mesh shape over here. Let's see. When we're finished with that, return point max, point min, and we can copy and paste and do basically the same thing for point max, for GetMax. Remind me though, did I at any point write a minimum or maximum? It doesn't look like I did. I didn't write a minimum or maximum method for any of the vector functions. You can totally do that if you want. I don't think I'm really going to need to at any point. I'll go over some additional, occasionally helpful vector methods at the end of the video. Like every time I think I'm done with those, something else comes along and makes me want to write another set of vector like methods. Where's ob? Okay, so GetMax is going to have to be basically the same thing in reverse. So point max is going to be these values. Point max is going to be the maximum of each of those. And instead of initializing point max to positive infinity, we're going to initialize it to negative infinity. I've realized that in the getMax function, the default value being negative infinity is a little bit counterintuitive, but that's how the math works out. And lastly, in call transformed model, we have ourselves a... Do we have ourselves a like get bounding box method? We do not have a get bounding box method. All right, well, I can write a get bounding box method, which will just give you a call ob for a transform model, and from there you can get the min and max of that. In my notes, I have written down that the GetMin and GetMax method for a transform model will be the min and max of the bounding box, and not necessarily the min and max of like a tightly fitting bounding box around the transform model itself. But this is going to be significantly easier to compute, and it should be close enough in most cases that it won't be like utterly outrageous. Let's say static get min. It's going to be a method to firstly get an ob, which encompasses a transform model. I'm going to say var transform is going to be self.get transform matrix. The ob, which we're looking for, is going to be a new call ob. Our position is going to be transform.mul point self.mesh.bounds.position. That's a bit of a mouthful. Our size is going to be self.mesh.bounds. Is it size? Did I make it size or half extents? I can never remember. I think it's size. I think I went with size because it's a shorter word. And our orientation matrix is going to be transform.get orientation matrix. And from here we can say return ob.getMin, and we can We can do the same thing for GetMax. Say ob.getMax. I'm going to... Why do you not like... Valuation order of function calls and argument are not guaranteed. Alright, you know what? Feather, that's really one of the less helpful messages. And there's in some rare cases it matters. We're calling a function or a method changes the state of things, but most of the time it doesn't. So, just from looking at this, you should be able to tell that get the min and get the max of a transform model is not going to be super efficient. Because we have to get the transform matrix, we've got to do a bunch of math, we've got to construct an ob, we've got to get the min and max from an ob. Definitely not nearly as efficient as, for example, get min and max of like a sphere. It should be possible to be able to, instead of doing this, get the min and max of the mesh bounds and multiply those values by the transform matrix, but I have not sat down to rigorously test out that theory. My math instincts tells me that there should be a way to do it, but I have not sat down and done the math and like worked that out for sure yet. I definitely feel like there should be a more efficient way to do this than what I'm doing here.
Hey.
At the very end of the series, when I make a video on optimizations, that'll probably be one of the things. There's going to be a lot of things in that optimization video. So I believe that is all of the major changes I wanted to, like all the major additions I wanted to do for shapes. Shape, get min and max. So I think it is time to close a bunch of tabs. Everyone's favorite part of development is when you get to just mash Control W. So I've been recording for almost 45 minutes of real time in this video, and I'd like to start wrapping it up soon. I definitely don't want this to go on for an hour, and I don't foresee like a logical stopping point anytime soon. So I know that the setup videos tend to not get a lot of traffic compared to everything else, but this is going to be yet another setup video for spatial hashes and laying out some ground rules and figuring out what our API here is going to look like. Next time, I will be getting to adding and removing things from spatial hashes, and if there's time after that, I will get to actually detecting collisions against them. Detecting collisions themselves is pretty easy. Raycasting into them is a bit of a separate matter. It's always the raycast that gives you more trouble than I really expect there to be, but that's going to be that. So, my name is Michael. I like Wizards and Dragons and making games. If you want the code for this, look for the GitHub repository down in the video description. This is going to be 0.32 apparently. Alright. This thing is going to have a runtime longer than, like, a lot of my Let's Plays. I try to post about 2 game dev videos a week, one tutorial like this, and one Let's Make a Game, currently a 3D wizard game, which I'm currently, interestingly enough, using to basically dog food my own collision system to see what its strengths and weaknesses are. So if you're interested in any of the weirder parts of GameMaker, feel free to subscribe. I have a Patreon, so if you want to contribute to the channel, links to that can be found in all the usual places. I hope you all find this useful, and I will see you all later. Special thanks to Zenjamin, VitroV, Squarecrow, Sindra Larson, Manta Ray, Harold Guidry, GameMaker, Edward Holt, DJ Gibbles, and Army Armbuster for supporting these videos. If you want to contribute to the channel, head on over to the Patreon page down in the video description to join the fun.